one of four authors of this report. The other four are Bill Bordas from William Bordas Associates, Jim Muir from ABS Consulting, and Graham Smith of Berlin Consulting. And all four of us are actually present, and the other three will also be participating in responding to any of your questions in the Q&A throughout the course of the presentation. Now, the structure of the presentation is essentially indicated here, and it's going to be split into three parts to make it a little bit more digestible. Essentially, the first part will be talking about the kind of characterization of the technology and of the issues associated with building automated technology. And this will include the definitions of building automated technology and the related devices, but also discussion of human factors, supply chain, building life cycle, and procurement-related issues. So we'll pause briefly at the end of that section, and the team will then respond to any questions for clarification that you've put in the Q&A up to that point. And then we will go into the second part, which is the deployment and savings potentials, where we talk about how we've characterized the European building stock, the penetration of building automated technology, building energy management systems, and home energy management systems, and then the findings from three long-range scenarios that we've developed in terms of the energy, economic factors, and CO2 associated with different levels of deployment and different levels of efficiency in the way that the services are actually provided. And then lastly, we'll again pause after that section, and then lastly, there will be a discussion of the barriers that are existing currently in the marketplace and of recommendations that we've put forward to help overcome some of these barriers and a set of recommended actions. So without any further ado, I'll just jump into the first part, which is characterizing the technology and issues. This is an different time to come into the understanding of what is encompassed within this area. The terminology that we've been using is BAT for building automation technology, and this includes any kind of automated controls from standalone thermostats and time switches to the most advanced technologies. We are using the term BMS to apply to all forms of building management systems, which include a range of building maintenance functions to a central point or points, including to the heating, ventilation and air conditioning systems. But their functions also include, and it's important to understand the much broader range of functions that they encompass. They include security and access control. They can include fire and safety, building management systems, and lighting controls. BEMS stands for Building Energy Management Systems. And what is found in practice is that most building management systems have the capability of energy management, but not all are set up or used in this way, even if they have the inherent capability. So that we're using the term BEMS, therefore, to refer to a BMS that is definitively set up to manage building energy performance. And similarly, home energy management systems are essentially building energy management systems designed for use in the home. So when we use the term BEMS, we're referring to buildings in the service sector or non-residential buildings, whereas when we use HEMS, we're referring to home energy management systems. Now, the controls themselves can operate all of these services here. They operate the mechanical heating and hot water systems, mechanical ventilation, the cooling and air conditioning, the natural ventilation systems, particularly motorized windows and dampers, and things like motorized shading, lighting, including timing, occupancy detection, mood settings, etc. Electrical systems, including time control and demand management and standby. Metering and monitoring systems, which include heat and flow meters when appropriate. Communications, safety and security systems, and services to special areas and equipment, for example, server rooms. Now, the principal energy end uses and energy savings opportunities through the deployment of building automated technology and building automated controls are listed here, more or less in order of importance. heating is the most important for the European building stock, followed by hot water, ventilation, cooling, humidity control, lighting, and then these other functions are listed further below. In principle, the benefits of building automated technology, if they're correctly designed, installed and operated, they will control building services installations to provide good indoor conditions and services while reducing energy consumption and running costs, and ensuring equipment operates only when, where and to the extent actually required. By doing this, it will also reduce ventilation and cooling requirements would arise when heat-producing equipment is used unnecessarily. It also supports monitoring systems and optimizing their performance, will provide advice of problems, providing not just failure alarms but alerts to wasteful and unintended operation, and reduce levels of wear and tear and the costs of maintenance, repairs and replacement. The system's hardware involved includes sensors, evidently, and these provide analog signals for temperature, humidity, pressure, etc. to controllers and outstations, which I'll explain in a minute. Thermostats, humidistats, pressure switches, which either perform control functions directly to plants or via valves, etc., or provide digital signals to outstations and controllers for limit functions. Actuators, which modulate valves and dampers, etc., and via analog or reversible motor signals. Controllers or outstations, which receive the signals from sensors and or send signals to plant and actuators. And these can be single purpose, i.e. a domestic heating programmer, or a temperature controller for a fan coil unit, or multifunctional, for example, a typical building management system outstation with a number of digital and analog inputs and outputs that can be programmed to suit the specific installation. And there are also supervisors which link to the network and allow the status of plant and outstations and controllers to be monitored and reset if necessary via graphics and trend logs and similar forms of presenting information. The devices users include timers and programmers, which range from straightforward on-off devices through those that are programmable to allow different day, night or hour-by-hour settings throughout the day. They can also vary by the day of the week or the year. Room controls to register a request, for example, light switches or dimmers or push buttons to activate heating or ventilation for a time period or until there is no occupancy. Occupancy sensors, which evidently detect whether people are in a space via presence detection to switch equipment on when people arrive, or absence detection to switch it off when they leave. Then environmental sensors, which detect, for example, light levels and control the amount of artificial lighting and shading. Temperature, which can control the heating, cooling, ventilation systems. Humidity, which is controlling the ventilation and air conditioning as well, and air quality, which is also controlling ventilation systems. Now, as part of the Energy Performance in Buildings Directive technical effort, which involves building a large suite of European standards to enable whole energy performance to be calculated and derived, there was a standard developed, EN 15232, to provide guidance on how to include building automated control and building management within the whole building energy impact assessment method developed by the EU. And this includes a detailed list of the control, building automation and technical building management functions which have an impact on building energy performance. It also has a methodology to enable the definition of minimum requirements regarding the control, automation and technical building management functions, and it has detailed methods to assess the impact of these functions on the energy performance of any given building. And these methods facilitate accounting for the impact of the presence of these functions in the calculation of whole building energy performance ratings. There's also a simplified method to get a first estimate of the impact of these functions on the energy management of typical buildings, which of course could be used in the kind of pre-design stage to consider the relative value of adding such capability. But as our study makes abundantly clear, and as work in the field is exposes very clearly, the whole savings proposition from building automated technology and controls is not just contingent on the technology itself. The interactions with human beings and the way human beings actually set these devices up and use them is absolutely critical to the overall outcome and to the whole way that the building energy services are actually being configured in the first place. So while a successful building is one that meets the business requirements of the owner and the occupier, works well for its occupants in providing a pleasant, safe, comfortable environment, while minimizing its environmental impact, energy use, and carbon emissions, what is actually found in practice is that building automation technology often fails to deliver its full potential for a whole host of reasons, including that those specifying the system have a limited understanding of how it will be operated, which can be compounded by a lack of building operation and maintenance teams, or lack of training of the operation and maintenance teams on the operation of the building services engineering systems and the building automated technology that is intended to control and monitor them. And so in spite of its undoubted potential, which we'll get onto later in this presentation, the advanced control and monitoring technology does not inevitably produce good results. And in fact, time and again, studies of building performance and use reveal that controls can often create problems too, and sometimes these can be so severe that occupants and management are confused, and energy and other operating costs may even increase in relation to simpler, more straightforward systems. Thus, there's therefore a need to promote not just the adoption of advanced controls, but the adoption of appropriate and effective controls that actually work, including addressing the factors for success in their deployment, which are essentially human factors in many regards. So the opportunities and barriers are both technical and managerial, and the strategies and policies of governments and business leaders for energy and carbon saving with advanced controls are not going to be realized without recognition that understanding the control technology alone is not enough to realize its full potential. The specifier, for example, also needs in-depth understanding of the systems to be controlled. Engineers and technicians need to be educated at all levels, not just about the technical aspects, but on how to achieve the benefits in practical situations. Appropriate motivational training and mentoring for designers and operators is very important, as is having competent, well-trained operation and management technicians with a desire to deliver the benefits that can result from the appropriate applications of the technology. And operation and maintenance service contracts that reward the service provider for using the building automation technology to limit energy consumption to the level necessary to deliver the occupier's business plan. Given this, we've concluded that focus should be given upon the following human interface operation considerations, which can be delivered individually or as part of a continuous commissioning program. Now, we have top of this list continuous commissioning, which I'll talk about a bit more in a minute. But briefing and the building life cycle, best practice procurement, occupant user feedback, design and implementation, lifetime product management, operation and maintenance, performance-based service provision, and real-time energy monitoring. And I'll come on to discuss those in a minute. Now, this is a figure that actually comes from a report put out by the Carbon Trust. And it just shows in the non-domestic building sector the variety of actors involved in the supply chain and end use of a building. And when we consider all of these different actors, all of who have a role to play in what may happen with regards to not just whether building automated technology is actually installed and operated and how it's done, but whether the systems that it's designing to work with actually can be controlled or not. We start to understand the complexities involved in ensuring that there is actually a reliable service provision being given in this domain, because there are a huge number of players involved who all have some part to play in the way that the eventual outcome which is actually realized. And any system delivery or service delivery has to basically function across this array of actors and ensure that none of them prevents critical things from happening, and that ideally all of them actually promote good things happening with regard to their installation, deployment and operation. So this is, when you consider this array of actors, it becomes more apparent why it's not so straightforward to always actually put a good system in and have it operating as was intended. I'll just move on to the next slide. This slide shows what we consider to be good practice in the building life cycle, and essentially shows the continuous commissioning component on the right-hand side, linked in green here, to the whole building life cycle going through the middle, from operation down to refurbishment and replacement of a building if required, linking to on the left-hand side, on the red flow part of the diagram, the whole briefing, feasibility, design, implementation and commissioning side of any new refurbishment or a replacement building. And on the right side, we can see that essentially with continuous commissioning, where you are involved in energy monitoring, optimizing, targeting and reporting performance back into this loop, that ideally one would have this level of information that would be reforming all of the decision making on the left-hand side as it occurs. And by doing that, outcomes are likely to be greatly improved than when this green part of the loop is not actually present in the process. Which leads to the notion of best practice procurement, and this is a flow chart showing one vision of this. And procurement is, of course, quite a complex thing, and it can vary from different business and enterprise and building types to another. But this is one attempt to kind of capture the process. And we see at the beginning of a brief, you have the organization's business needs being reflected into the outline of a brief. And then ideally, you would bring in, from the demand side, you would have the facility management and the managers and the operation and maintenance teams providing their input, in conjunction with, on the supply side, the project management and the design and build and supplier input, going in to form a detailed brief, which would then receive client approval before design, implementation and commissioning. The onset of occupation, beneficial occupation, i.e. the building is actually being used for its intended purpose, followed by a period of at least 12 months of following the date of beneficial occupation, during which the supply and demand side collaborate to validate the design intent and ensure that the building services engineering and the building automated technology are fine-tuned to deliver the optimum of cost and value for the occupier. And ideally, if this were to happen, then full handover would happen after that period, and there would be confidence that the design intent was actually being achieved in practice. But of course, this suggestion here of best practice procurement is not actually what occurs in a great many of the circumstances in practice. Now, this is the first natural stop point, and I can see no comments in the Q&A at the current time, so I'm assuming everybody's quite happy with what I've said so far. So I think I shall just carry on. Is that okay, Dida?
Yes, Paul, that's okay. I just want to mention that I got a message from one of the participants that the audio is not always very good in quality. So if other people are experiencing the same problem, please let me know via the Q&A window so that we can sort out if this is a general problem. But in the meantime, just go ahead, Paul. Thank you. Okay, great.
So now I'll just come back to that. I'm now going to be talking about the deployment and savings potentials part of the study. The first part of this was characterizing the European building stock, and we reviewed the literature and a lot of data that was available. And we decided to characterize the service sector buildings into the following principal groupings for energy modeling purposes, which is basically offices, retail outlets, education establishments, hotel and restaurants, healthcare sector buildings and other buildings. And for the residential building sector, we split them into single family and multifamily. And the reasons for doing this is partly driven by the quality of the available data, which was the highest quality when split up this way, but also to do with the homogeneity of behavior and type of uses of building automated technology that one sees in these different building types. So this is how we actually ended up dividing up the European building stock. When we look at the distribution of building floor area by building type, it says projected. It was based on data which was 1 or 2 years older than 2013, but we had time series trends in many cases, and so we projected it forward through to 2013 to come up with this figure. And from this you can see that the service sector accounts for 26% of the entire European building stock by floor area. And of this, the office sector and other are the largest, there's 6% and 7%, education is 4%, and then you can see the other splits in terms of total floor area. Then in the residential sector, the multifamily accounts for just under a quarter of the total building stock by floor area. And then the biggest proportion is single-family residences, which are 50% of the total. When we look just at the service sector building floor area, split this into types and the distribution by size in meters squared, this is what you can see in these graphs. And so we did try to take account of size distributions in the modeling as well as types when we made our projections. These obviously have some impact on the viability of different technologies and services which can be installed. So it depends on a number of factors, but size is one of them. When we look at the actual distribution of, in the service sector buildings, final energy consumption by end use in million tons of oil equivalent, as you can see in this graph, we see that space heating accounts for just over half of it, water heating 14%, and then you have lighting as the next larger proportion of any one single end use at about 10% of the total, other electric 12%, cooling 7%, cooking 4%. It's important to understand, of course, this is final energy consumption, and for you to reflect this in primary energy terms, the electric components would become a lot larger, or the electric specific components be multiplied by about 2.5 to bring that up to a bigger proportion of this pie chart. When we look in the residential sector, we can see that, again, space heating dominates, but it's even more dominant. It's 64%. Water heating is also more dominant, it's 18%. And then you see these other applications here with appliances 8%, lighting 3%, ventilation 2%, etc. Again, the same remark applies with regard to primary energy for the electricity-specific applications. Now, when we try to assess the penetration of building automated technology, building energy management systems in the service sector and home energy management systems in the residential sector, essentially what we found is that all service sector buildings in the EU have some kind of building automated technology installed. And the baseline will usually involve having at least thermostats, time switches, and in many countries, optimum start control. The penetration of building management systems as distinct from building energy management systems is probably about 90% of the larger EU public and commercial buildings, but is very low for smaller public and commercial buildings. However, only about 50% of the installed BMS have more than an elementary energy management capability actually operational. So overall, we've estimated that about 26% of total public and commercial building floor area in the EU is thought to have operational building energy management capacity installed, as opposed to the building management services capacity. Note, however, that there is, of course, considerable uncertainty about this, and the data on the actual penetration of the BAT, BMS, BEMS is somewhat scarce. From an analysis of a lot of data sources, we derived a formula for the average penetration rate of building automated technology, building energy management systems in the service sector, and this shows what it is here as a function of, so it's showing the sales per capita per year as a function of GDP per capita on average for the European building stocks. Now what we find is that the average per capita sales in some economies are about 20 to 30% above the values predicted. For example, Eastern Europe, the UK and the Nordic countries are above the average projected by this. The sales in some are below by 10 to 35%, France, Italy, Spain and the Benelux, and yet sales in Germany are about 80% above it. So Germany is the outlier and has a much higher penetration for its GDP per capita level than is the European average. And this table shows the penetration. The penetration varies by service sector building type. So you can see here the share of the floor area fitted with BAT BEMS per year, and it's highest in hospitals, which are relatively high energy intensive, so it makes sense that that should be the case. And it's lowest in educational buildings and then in retail. We also have our derived figures on the cost to install and commission the BAT BEMSs in euro per meter squared on average in these building types, and the average energy use per year by meter squared for these building types as well. And all of this is described more in the full study. And when we look at the drivers of the penetration of building automated technology and building energy management systems, there is obviously when there's new build, refurbishment, renovation and refitting, that is an event which is an opportunity to install BAT and BEMS. And so there is a strong correlation between the market and the frequency of new builds, refurbishment, renovation and retrofitting. And that in itself means that the market will tend to follow those cycles if things have been stabilized. However, there's also other drivers taking place. There are technological innovation and greater value and improving value added from the service offerings. There are energy price impacts, currently increasing awareness of energy costs and carbon footprints, increasingly proactive regulatory measures, and other policy incentives which can all drive the market. And so while we're finding that the traditional drivers linked to the renewal replacement cycles of buildings, which are strongly tied to economic growth and hence have been depressed, very strongly depressed in recent years, the strengthening trend in the remaining drivers has tended to more than overcome this in the last few years, and sales have continued to grow despite the depression in the general economy in Europe. So we took all of these factors and we put them into our energy model that we developed. It's a detailed bottom-up energy model, split by all the different types of buildings, split into floor area, distributions, split by energy end uses into those. And then we examined 3 different scenarios. The first one being a reference scenario. And this essentially assumes a continuation of current trends regarding the adoption and installation of building automated technology, building energy management systems in the service sector, and the home energy management systems in the residential sector, and assumes no significant improvement in the installation and management procedures. The reference we took here was the International Energy Agency's new policy scenario from their 2012 World Energy Outlook, which is reasonably aggressive on the decarbonisation of the European economy as well. So when we look at CO2 savings later on, we should bear in mind that the reference scenario is already reasonably aggressive in that regard. The optimal scenario, which assumes that there is an optimal level of installation and operation of building automated technology, building energy management systems and home energy management systems from a end-user cost-effectiveness perspective. So this is what you would call in many cases a kind of least life cycle cost scenario, where you would be optimizing the economic performance. And then assuming there were no other barriers to deployment and to successful operation of the systems. And then there was a recommended action scenario, which is between the reference and the optimal scenario. And this assumes that the recommended actions outlined in the last section of the report are fully followed and aggressively followed, and that the building automated technology, or the building energy management systems and home energy management systems, are procured, installed and operated as would be expected were those recommended actions fully implemented. What this does in terms of driving penetration in the service sector is shown here. And we can see that penetration in 2013 starts as about 26-27%. And then under the reference scenario, it would rise by 2035 to just under 50%. Under the recommended action scenario, it gets up to pretty much 100% by 2033, rising slow, following the reference scenario to begin with, but after a few years going more proactively. And in the case of the optimal scenario, that trend towards 100% penetration happens much faster and is fully completed by 2025. The expected energy savings across the European building stock in the service sector under the optimal scenario, they peak in 2035 at 50 million tons of oil equivalent, which is about 20% of all EU service sector building energy consumption at that time frame. So that is the envelope of opportunity that we've calculated, essentially 20% in the service sector. Under the recommended action scenario, the savings come to 40 million tons of oil equivalent by 2035, and that's just under 17%, so 16.5%. Compared to the reference case. And bear in mind that the reference case is already assuming more or less a doubling of the savings from this in any case over that time frame, because the market is not static in any case. And then the cumulative savings in final energy consumption over the time frame under the optimal scenario are 740 million tons of oil equivalent under the optimal scenario, and 500 MTOE under the recommended action scenario. And these cumulatively over the period are essentially 15% and 10% of the cumulative building energy consumption under the reference scenario from 2013 to 2030. And this shows the profile of those savings under the optimal scenario and the distribution by fuel type. And here we see a slower rising and lower final point, 40 instead of 50 MTOE under the recommended action scenario. And we look at the residential sector and the penetration of home energy management systems. The large majority of residential buildings in Europe have some kind of building automated technology installed, even if it's as simple as a timer control thermostat for the heating system. However, a much smaller proportion have a modern home energy management system coupled to intelligent and demand-responsive controls. The national implementation of building codes, driven by the Energy Performance of Buildings Directive, are increasingly becoming key drivers of the level of functionality and sophistication of controls that are installed in new or retrofit buildings. But even these fall short of requiring home energy management systems to be installed. So a more typical requirement under current building regulations would be to specify the use of thermostatic radiator valves on all heat emitters, programmers, and room zoning valves, but not be going beyond that level of functionality. And here we show the equivalent table that I showed you earlier, but this time for the residential buildings, showing the total floor area, showing the current sales on per meter squared per year on average, the sales of home energy management systems, which are a small proportion of that in euros per meter squared, And then the share of floor area fitted with some kind of building automated technology per year is between 3.6 and 4.9%. The share of floor area fitted with home energy management systems per year, which is a much smaller percentage. It's only 1.1% in multifamily residences and about 1.4% we've estimated in single-family residences. And then the cost to procure, install, and commission building automated technology only, which is between 6 and 5 euros per meter squared, and the same for home energy management systems, which is between, well, roughly it's around about 12 to 13 euros per meter squared from the estimates we have made. Under the three scenarios, again, we see very similar sorts of penetrations, but they are actually lower than under for the service sector for a variety of reasons, largely to do with the scale involved, but also the complexity of working with the different actors concerned. So while under the optimal scenario, it is again cost-effective, essentially in all residences, to have some form of home energy management system installed eventually. And so this is what we assume under this scenario, the optimal scenario would happen by about 2028. Under the recommended action scenario, even by 2035, there's only about 85% which actually have home energy management systems in, whereas under the reference scenario, it's just over 40% by that time frame. The expected energy savings in the residential sector are larger than they are in the service sector under the optimal scenario. They're 98 million tons of oil equivalent as opposed to 50 for the service sector. Under the recommended action scenario, though, they're much closer to the service sector levels. It's 49 million tons of oil equivalent as opposed to 40 for the service sector. And the cumulative savings are about 1,350 odd MTOE under the optimal scenario, and about 500 MTOE under the recommended action scenario, which are about 13 and 5% respectively of the cumulative building energy consumption under the reference scenario in the residential sector under this time frame. And here we can see the savings profile over time for the optimal scenario, again split by fuel type, and for the recommended action scenario. And when we put those for all the building sectors together, we can see the two, as I was mentioning earlier, for the service sector and residential sector and recommended action scenario, rather similar levels of savings, so both be equally important. And for the optimal scenario, considerably higher savings in the residential sector, that for various reasons we think that's going to be extremely difficult to achieve over the full time frame we're talking about. Now we come to the discussion of the incremental investments that would be required. Now, the cumulative total investments in the service sector over the full scenario period would amount to 44 billion euros under the optimal scenario and about 41 under the recommended action scenario. Although the totals are rather similar, the profile of incremental investment is much higher initially for the optimal scenario than for the recommended action scenario, which means that the cost effectiveness within the time period of the scenario is higher because, of course, they're reaping the energy savings from those investments, whereas in the case of the recommended action scenario, a lot of those energy savings will occur post or beyond the end of the scenario period. The incremental investments peak at about 4.6 billion euros under the optimal scenario per year, before dropping sharply. This is against the reference scenario. Whereas in the recommended action scenario, they peak at 2.5 billion, but this is sustained for a much longer period. And in both cases, they eventually drop away to zero compared to the reference scenario, as maximum penetration is reached and the market becomes a replacement market. And so you can see this incremental investment profiles compared to the reference scenario shown here. When we look at the bill savings associated from this, again, we can see that the ramp up is faster under the optimal scenario, of course, and it's slower under the recommended action scenario. But of more interest is that the bill savings are so much higher order of magnitude than is the investments required to actually realize these savings. And this means essentially that there's a highly attractive value proposition from a cost effectiveness and economic efficiency perspective. So under the optimal scenario, the savings in energy bills rise to 51 billion in 2025 and then rise more slowly to 56 billion at the end of the scenario period. Whereas under the recommended action scenario, the bill savings peak at about 48 billion at the end of the scenario period. And the cumulative total additional bill savings are about 830 billion euros under the optimal scenario and about 620 billion under the recommended action scenario. And these are 18.8 and 15.3 times as great respectively as the magnitude of the additional investment. And the average payback periods are very short, at only 1.5 years on average, despite variation across building types and economies. When we look at the residential buildings, the cumulative total additional investments over the scenario period under the optimal scenario are about 160 billion euros and about 95 billion under the recommended action scenario. And the annual investments peak between 11 and 12 billion from 2017 to 2028 under the optimal scenario before dropping sharply. Whereas in the recommended action they peak at about 5 billion by 2019 and remain near that level to the end of the scenario period. And we can see the profile here. And see that in fact the investments are carrying on with the recommended action scenario because it hasn't reached the full 100% penetration level by the end of the scenario period. But again, when we look at the energy bill savings, we can see that they are very much greater than the incremental investments required, as shown in this figure. And the savings in annual energy bills rise to just under 106 billion in 2029 for the optimal scenario, and remain more or less at that level, whereas to the end of the period. Whereas in the recommended action scenario, they're about half that at 56 billion at the end of the scenario period. And the cumulative total energy bill savings are just under 1,500 billion under the sort of 1.5 trillion under the optimal scenario, and about 560 billion euros under the recommended action scenario. And these are 9.2 and 5.9 times respectively as great as the magnitude of the additional investment over the period. The average payback periods are much shorter than the service life of the technology, but they are longer than you'll see in the service sector buildings. So when we look at this cumulatively for both the service sector and the residential sector, the two big area parts of this chart at the top show the bill savings over the time frame, and the lower parts show the investments. The investments are put on the right axis. The bill savings, which are a different order, a factor of 10 difference in their magnitude, are on the left side of the axis. So there is a very, very significant difference in these two. And showing that there is a tremendous economic value proposition from greater deployment but much more effective operation, installation and usage of building automated technology. So in summary then, when we put in the CO2 figures as well, we find that the optimal scenario for all building types leads to over 2,000 million tons of oil equivalent cumulative energy savings and about 5.9 gigatons of CO2 savings over the time period compared to the reference scenario. And this equates to about annual savings about 184 billion tons of CO2 in 2020 and 380 in 2035. Whereas under the recommended action scenario, it's about half of this. It's 1,000 million tons of oil equivalent of cumulative energy savings and 3.4 gigatons of CO2 compared to the reference scenario, with annual savings of 96 million tons of CO2 in 2020 and 260 million tons in 2035. Now, to put this in some kind of context, The European Commission has estimated that the annual savings from the EU emissions trading scheme are about 187 million tonnes of CO2 a year. So these figures are in a similar order of magnitude that could be achieved from this area to what the Commission recommends is currently being saved from the emissions trading scheme. So the total extra cumulative investment is about 136 billion that will be required, an average of 6.2 billion per year. But these are 9 times less than the value of the resulting savings in energy bills, which are about 1,187 billion over the period, at an average of about 54 billion a year. And that brings me to the end of that section. So again, I can't see any comments in the Q&A.
There has been some questions this time, Paul.
Okay, great.
But if you don't see them, I'll just read them out loud and let you the answer. Okay, so there was a question from Colin Timmons. Has your baseline study looked at building codes in various member states relating to the building automation technologies?
Yes, it did, but I wouldn't say it did it in as much detail as one would like. So we did when we were looking at the reference scenario, we essentially took that into account, and then we took the incremental effect of that into account. But I don't think we've done as thorough a job as one would like to have done on that. It's not like we've gone into every one of the 27 EU member states and done a detailed dive into all of their building codes. We just looked at the main ones and used those as our barometer, if you like.
Okay, thank you. There was another question, what the source of data was on European building stock?
Well, it comes from several sources, but I would say one of the main sources is the BPIE database, which I'm sure many of the people on here are familiar with. And we could, I think that's actually referenced in the report, but if people would like to know more about that, we can send the contact details on the website for it. In fact, anybody from BPIE is on the call at the moment. I don't know if somebody was due to be, then perhaps they could actually load that their website onto the. In fact, I can't see anybody from there on at the moment, unfortunately. So we'll try and put that up before the end of the webinar, or send it around to people afterwards.
Okay, thank you. The same person also asked regarding the penetration, is this based on all building stock in service sector and for the European Union of 27? If so, it looks very aggressive as an estimation, since the activities in renovation or refurbishment will need to be very high to reach that projection.
I'm not sure which penetration level is being referred to, whether it's under the reference scenario or under the other scenarios, the policy scenarios. The reference scenario is basically taking the projected trends from what we've seen, following the formula that I showed you in the service sector buildings case, but also following projections from what has currently been observed. As I said, there are issues about the quality of data, but this is the best values that we could derive based on the available sources that we have access to. And it seemed to tally as well. We discussed this with a number of people in the field, and it seems to tally with their understanding as well. But we'd sort of be interested in people's comments on that. In terms of the more aggressive scenarios, I completely agree that the optimal scenario, the optical scenario is a theoretical scenario in the sense that it assumes that everybody more or less goes out tomorrow and does what is in their own economic best interest to do. And there's all sorts of reasons, as we'll get into the next part of the presentation, why that's not likely to happen. So it is really pushing the envelope in terms of how rapidly the deployment could occur. I think the recommended action scenario is more or less kind of doubling the rate of installations that are currently would be expected to occur under the reference scenario. And we don't think that that is unrealistic. It's aggressive, and it does assume a very strong set of proactive activities, but we don't consider it to be unfeasible. But I'd certainly be interested in people's perspectives on that.
Okay.
Any other questions, or should we move into the next
there was
part?
another question. I just also published a reference from Roland Ullman to standard ISO standard on the Q&A, but it's just a reference, not a question. Another question was raised by Alain Anglade. Did you assess the already installed base of building automation technologies and BEMS in the European Union?
Yes, we did. So that's forming our baseline that we are putting in there, and that's embodied within the reference scenario.
Okay. And the last question, what about the part, and you should be able to read it now, what about the part of the market for replacement of existing building automation technologies?
Yes, well, exactly. The two tables I presented talk about the rate of replacement that is currently happening, and you'll find those in the main report. So they deal with that question of what is the replacement cycle to some degree. I mean, it's a combination. What they actually are is a combination of the replacement market plus the new market, and both, of course, are happening simultaneously.
Okay.
What is the assumption on what a typical HEMS would comprise? Yes, there's quite a lot in the report which is talking about this. I mean, the HEMS would what it isn't is just a display of energy consumption. What it would include is the degrees of control. The typical HEMS that we will be looking at would essentially be HEMS to control the heating and hot water systems. It would not be also controlling lighting and other services, and that's to do with cost effectiveness at the current time in most home energy applications.
Okay, thank you. And there's a final question from James Warren. I let you read it yourself.
Yeah, I'm just, hang on, I need to advance a little bit. Well, yes, this question about the rate of return and the earlier statement that BAT is not delivering on the available and savings potential. Because what we're finding in reality is that while the returns that I was talking about were based on properly installed, correctly configured, properly specified systems which would be installed and operated in an appropriate manner. Of course, what I was stressing earlier on is that that is often not the case at the current time for a range of different factors. And therefore, the optimal scenario is assuming that all of those problems just get waved away, which of course is not realistic. The recommended action scenario is assuming the set of measures which we're going to be discussing in the next part of the presentation are actually fully acted upon, and I would say on top of just the recommendations you can sort of see as being somewhat headlines to a much broader set of activities. But they are acted on in a pretty aggressive sense. And they then ameliorate a lot of the problems and actually realize a much larger part of the potential than is currently happening. And this is essentially why we think that for a range of reasons, that the cost effectiveness will improve substantially.
Okay.
I'm wondering if that's a
Thank
good cue for me to now present the next part, Dieter.
you. We're back to the slides. Go ahead.
So now we come on to the barriers and recommendations component of the presentation. And I hope everybody realizes, of course, that in the time period available, it's not possible to go through everything that's in the report. So you'll find more depth on a lot of the aspects already raised within the report. The first thing I'm going to show here is a generic set of barriers to energy savings. And this is a table that I actually helped to derive for the International Energy Agency for their World Energy Outlook in 2012, where they had 3 chapters on energy efficiency. And we looked at, based over many years of experience of considering these issues, what the generic barriers were to energy savings, what the effect of those barriers were, and what some of the remedial policy tools are to help address them. Because the question which always comes up with energy efficiency, which is, if it's so cost effective, why doesn't it happen automatically? And this is a summary of some of the reasons why that is the case. Now, interestingly, this generic set of barriers, of them, nearly all of them apply to, in varying degrees, to the building automated technology and energy management domain. So firstly, the visibility barrier. Energy efficiency is not measured, and that certainly applies in the building stock. It's not, the energy consumption may be measured, but energy efficiency is not necessarily measured, and that is a barrier, and therefore it's invisible and can be ignored. Energy efficiency is not visible to end users and service procurers. It's another barrier. That there is, in terms of priority, there's a low awareness of the value proposition among service procurers, and so while that value proposition is definitely rising, awareness is definitely rising, it's still relatively low compared to the actual magnitude of the proposition. There are certainly problems of split incentives. The classic one in buildings being the landlord-tenant situation, where the landlord pays the or would commission and pay for any refurbishments of the building, whereas the tenant would be paying the energy bill, and so there's a division of incentives. But there are many other split incentives which apply as well. Another classic one for buildings is that the owner, even in owner-occupier situations, that the period of owner occupation is much shorter than the lifespan of the building stock or of the equipment within it in many cases, and so that there is a weakened incentive for any one owner-occupier to actually optimize the performance over the life cycle of the services that we're talking about. There's scarce investment capital and competing capital needs, and this is a barrier which is nearly always cited when being considered, and people are very conscious of this, that any investment made in energy efficiency measures is competing against competing investment opportunities. There is strong perception of risk, and that's not an unreasonable perception of risk as well, because risk is quite high at the moment in this domain of not getting the outcome that is actually hoped for, and therefore the return may not be what is hoped for from the investment. There are certainly big problems of capacity in terms of the limited know-how on implementing energy-saving measures, and there are major problems of fragmentation and underdevelopment of the supply chain. So all of these areas apply in the case of the field we're talking about here. And this table here shows some of the specific, sort of, if you like, kind of technology, service-specific barriers which apply in this domain. Problems of poor operation, inadequate training and status of building service engineers, inadequate control specifications, so that they don't actually meet the requirements. And another problem of having, which is not directly the control system's fault, but it's a problem that control systems have to deal with, which is that the systems themselves that have been installed in buildings may not be properly controllable. And this is due to problems of poor hydraulics, incorrect plant selection, etc., which can occur in the building stock. Other problems we see, poorly designed control interfaces, which can affect the user-friendliness of the systems, and problems of complexity, that the systems can be too complex for the users to manage. So focusing on some of these, the recommended actions we've put forward, and we don't consider them to be the definitive list. There are many, many other things which one could imagine, but we try to draw up a hierarchy of needs. Essentially, due to these problems, we've proposed a set of measures which will aim to increase the reliability of the savings from building automated technology, building energy management and home energy management systems, but also increase the adoption of them. But to increase the adoption of systems which work as intended and actually deliver the savings that are intended. And both actions are actually necessary from everybody who's involved in this domain, whether you are an end user and you're looking to get the savings from the services provided, whether you're policymakers looking to limit the energy dependency of the European building stock, minimize environmental impacts and improve overall macroeconomic performance, whether you are involved in the industry sector and you're a service provider and you're finding that while you have a great service and technology, that the levels of adoption are not as high as they might be because of barriers in the marketplace, because ultimately they affect service delivery and they therefore affect the value proposition and the repeat business that you might otherwise get. So all of these issues need to be addressed to build a kind of virtuous circle and create confidence and drive demand in the market. The measures essentially address promoting high-quality continuous commissioning when appropriate, promoting development of advanced data analysis techniques and route to market, which are complementary, building capacity among the building energy control service providers and engineers, strengthening interoperability and standardization, raising awareness in the market of the value proposition, educating and strengthening the supply chain, and overcoming first cost barriers and risk aversion. First set of these are to develop targeted financial incentive mechanisms, which are designed to both stimulate supply and demand of quality, automated technology, energy management services, at as fast a scale as can reasonably sustain without risk of market poisoning through unqualified service delivery. And it's very important that whatever service is being promoted does actually deliver the intended outcome. Otherwise, there will be backlash in the market, and there will be a market poisoning effect, and the savings will diminish, but also the repeat business and willingness to move forward will diminish as well. So while one wants to see increase in the scale of deployment, it has to be coupled with increase in the competency of deployment, so that the overall outcome is actually is being achieved, the desired outcome is being achieved. In order to achieve this, we also propose to make use and adapt existing policy levers. We could have imagined a whole group of entirely new policy levers, but when we looked at the available policy frameworks in the EU, and particularly in the Energy Performance in Buildings Directive and the Energy Efficiency Directive, we did find that there are a number of measures already there which could be built upon addressing the following areas, which are building regulations, public procurement, utility energy efficiency obligations, the cadre of qualified professionals, developing energy service markets, public sector buildings, building stock renovation, sub-metering, and demand response. So I'll talk about all of these areas. In the continuous commissioning domain, our recommendation is to promote high-quality continuous commissioning targeted at ensuring that building energy control is effective via capacity building, quality assurance, promotional and incentive measures, all of which will be designed to overcome market barriers and stimulate demand. And we note that if structured properly, early-stage capacity building and financial support can be reduced in time as continuous commissioning becomes more widespread and known in the marketplace, and its benefits become more widely communicated and disseminated, which would essentially allow a larger volume natural market to develop. So essentially we're seeing many of these things would be precursors to strengthening the existing continuous commissioning market to a more appropriate scale. And continuous commissioning is especially needed in large, more complex buildings. The advanced analysis techniques, there's been a significant increase in meter provision and sub-metering, yet relatively little is usually being done with the results. So that where sub-metering is available and analysed, it is often in isolation from the building management system, which actually controls much of the energy usage. And currently, recommended actions are often made by energy experts or those who present themselves as energy experts, many of whom may have little understanding of the complexities of effective modern building control systems, and this can lead to counterproductive advice. So with advanced analysis techniques that more effectively link the operation and metering size, they would help facilitate more objective and effective analysis of system operation and energy efficiency. And this could lead to improved fine-tuning of systems with effective feedback of the results. And our recommendation here is to promote the development of these advanced data analysis techniques and routes to market. And the tools will be of significant benefit in their own right, of course, but they would also complement continuous commissioning and associated factors in improving building energy performance. On the capacity building side, there are currently barriers due to inadequate specification and installation of building energy controls and automation systems, improper commissioning of them, and insufficient knowledge of the technology options and practices among building code and energy performance certification requirement designers. And so consequently, it's recommended that structured efforts be made to develop a supply of high-quality service providers through the establishment of dedicated training, certification, and accreditation efforts. And we do recognize, by the way, that some of these things are already happening to some degrees. It's really a question of how broadly and what scale. The recommendation is to build capacity among building energy control service providers and engineers through the establishment of dedicated training, certification, and accreditation, and the provision of practical and usable expert guides and tools to facilitate appropriate design, installation and commissioning of automated building energy controls. Strengthening interoperability and standardization. There is a strongly growing use of BACnet, but there are many problems with constrained interoperability of building energy services equipment and their control systems. And we feel that there's still a need for industry and government to work closely to address these issues, to ensure that appropriate communication protocols are adopted universally so that all systems can function together. And this is still a barrier to effective deployment and operation. So standardization of control strategy programming techniques and documentation of system operation is also required to facilitate improved skills transfer within the controls industry and assist understanding of systems operation by building service engineers and others who are responsible for system acceptance and ongoing operation. And our recommendation is to strengthen the market rewards for interoperable products by way of awareness building measures targeting the supply chain, product compliance, quality certification, and direct incentives. Educating the market and supply chain. There's a need to educate the market about the value of following up installation and commissioning with expert operation support through continuous commissioning. And both government and industry have a part to play in this process. Similar issues occur for the home energy management market as well, and the supply chain, where end-user awareness of savings potential and paybacks is very limited currently, and the value proposition is muddled owing to a lack of transparency and comparability in service delivery. And so our recommendation is that government and industry, both on the supply and demand side, work cooperatively to develop and implement a supply and demand side awareness-raising education and quality assurance program. In the field of finance and incentives, both financing and incentive packages are needed to overcome significant risk aversion and first cost barriers while rewarding good practice. So the incentives can not only just help buy down the first costs, and address risk aversion to the investments, but they can also help drive the market towards good practice by rewarding those that supply good practice. The recommendation will be then to develop well-timed and targeted financial incentive mechanisms designed to stimulate the supply and demand of quality services, products and services at as fast a scale as can reasonably be sustained without risk of market poisoning through unqualified service delivery, and simultaneously facilitate and promote innovative contracting and financing mechanisms that reduce upfront cost risk and tie the rewards to the successful delivery of downstream energy savings. Noting that given the vast scale of the cost-effective energy and bill savings that are achievable, it is appropriate for these mechanisms to be designed to be of a sufficient scale to help access to a large part of this potential. And given that that can involve some very large sums, it will be appropriate that a considerable amount of preparatory work would be should be done to design these schemes so that they really are cost-effective at scale and that they can be ramped up to scale. Now that brings to the question of adapting the existing policy levers. We have a recommendation that while provisions requiring the use of adequate controls in new build and renovations are necessary to stimulate uptake of energy savings controls, there needs to be a much greater reflection given to how they should be framed and specified to ensure they are clear, usable and encourage good practice within the Energy Performance in Buildings Directive. And in order to ensure that that happens, we recommended that an expert task force be established to prepare guidelines on these specific specifications and review and critique the existing specifications. So this is going back to the building codes we were talking about earlier. And to ensure that the recommendations reflect real application, we think the task force should include review from practitioners who would be expected to use the requirements and not just experts from the control industry or researchers. So once clarity on the optimal regulatory specifications has been established, then EU member states should be encouraged to move towards implementing them fully in their building codes and to monitor their implementation experience and ensure desired results are being achieved, making informed adjustments whenever that's not the case. And we think there's clearly a role here for the European Commission to facilitate coordination of this process. In terms of the Energy Efficiency Directive, I don't want to go into all the details of paragraphs 16, 17 and 18, but in the implementation of those paragraphs, we believe that there's an opportunity for all public sector renovation stimulated through these provisions to require the use of quality assured building automated technology and building energy management systems, products and services. And these should consider including strong requirements and incentives for the preferential procurement of continuous commissioning services to ensure best practice service delivery. So another recommendation is that the EU member states should take the opportunity when deriving plans to implement the requirements of paragraph 19 of the Energy Efficiency Directive to ensure the setting of appropriate public procurement specifications that drive demand for quality assured BAT BEMS products and services within the public sector building stocks. Again, on the Energy Efficiency Directive, for paragraph 20, which concerns the development of obligations, energy efficiency obligations for utilities, there is an opportunity here for this to be adapted such that it might provide a vehicle for financing of best practice of BAT, BMS, Home Energy Management System Service Delivery, it should be BEMS there, financial incentives, capacity building and related programmatic support within the National Energy Efficiency Obligations programs. And energy market regulators have a role to play ensuring appropriate quality assurance and incentive structures are in place such that real energy savings are being delivered through such mechanisms. On paragraph 24, which encourages energy audits amongst the SMEs, there is an opportunity to put in systematic programmatic support for continuous commissioning in the SME building stock and thereby develop continuous commissioning service capacity within that sector of the economy. In the Energy Efficiency Directive and also the Energy Services Directive, their revisions should consider elaborating requirements for sub-metering of dynamic plant, and also consider removal or amendment of any requirements that have unintentionally created disincentives to the installation of thermostatic radiator valves on buildings supplied by district heating networks. And lastly, that it's recommended that the clarification process alluded to in paragraph 33 of the Energy Efficiency Directive be taken as an opportunity to review the interaction between the smart metering requirements, sub-metering, and the building automated technology and energy management systems, as well as regarding access to billing information, interoperability issues, and the provision of energy services to ensure that the most effective metering requirements are being promoted. And then coming to the last measure in the Energy Efficiency Directive, paragraph 46, they should aim to build capacity among building energy controls, service providers and engineers through the establishment of dedicated training, certification and accreditation, and the provision of practical and user expert guides and tools which would essentially facilitate appropriate design, installation and commissioning of building automated energy controls. And this measure could also target the gap between system specifiers, building service consultants and systems integrators, so that the systems are correctly designed for controllable operation and robust control strategies are specified for the systems integrators to implement. And then lastly, there is currently a review taking place of the energy labeling and energy eco-design directives. And in the case of the energy labeling directive, there's an opportunity to consider whether it's appropriate now to amend the scope to address labeling for building automated technology, home energy management systems, and building energy management systems, noting that EU BAC, the Industry Association, already have a voluntary labeling certification program in place, but that is not within the auspices of the formal EU scheme at the current time. So there's an opportunity to look at that issue. And so that concludes the presentation, and I can see that we have a few more questions. Thank you, Didier, for bringing them up.
Okay. Let me first.
Maybe we don't have any more questions, actually.
Yes, we do.
Yes, we do. Yes. Okay.
Colin Timmins asked something about recommendations, that they are all through EED and EPPD, which are both implemented by individual member states. Does this not in itself present a significant barrier to the benefits, which assume the whole European Union being achieved in practice?
I think potentially it does, and so there will clearly be opportunities in the revision of the Energy Efficiency Directive and Energy Performance in Buildings Directives to look at the degree of robustness of the implementation of these measures, and in fact I'm sure those are already in the pipeline. The interesting thing that we noted when we went through these directives is that we saw that there were many places where, as you saw in the recommendations we made, where there were opportunities in the general wording to apply those actions which are required in the directives to the building energy controls domain, but they are not specified directly. There is no specific statement ever mentioning building energy controls within any of those articles of the existing directives. Now, in the meantime, we think there's plenty of opportunity for member states to actually look at these issues and to see that these are actually complementary within the spirit of what's being proposed in the different articles of the directives. But in future revisions of it, it might be very helpful were the directives to have measures which were targeted directly to the controls domain. And that's certainly something which I personally think would be worth looking at in those future revision processes. But we wanted to have a set of recommendations which would, as much as possible, work within the existing regulatory frameworks and build out from them when it comes to the policy domain. I mean, obviously there's a number of things which can be done in the private sector as well. And so this is why the recommendations are structured as they currently are, but clearly there is a queue to bring that in at some future stage. Yes, and Gambi has mentioned that the design of the EPBD is more of a performance-based code instead of a checklist form of regulation. That's exactly right, it is. And it's just that what one finds in practice is that there are many things that are that it's useful to have a checklist in the back of the mind when thinking about this. And I think controls were probably an area that was not the top of mind concern when the Energy Performance and Building Directive was first being put together. It came in through the course of the directive, but somewhere near towards the end. And of course, it's dealing with whole energy building performance, and controls are just one part of that, and they are one route towards an improved energy performance. It's just that there are clearly a number of areas with them that need to be addressed to ensure that they both don't get in the way to achieving expected energy performance of the buildings, but also are actually actively contributing towards achieving it, and that the actors in the field are fully cognizant of the opportunities which exist there.
Okay, thank you. Two more questions for clarification, I think more in the second part of your presentation. I'll put them up right now.
Okay, so how do we assess the energy savings? We essentially did this by looking at a range of case studies and looking at the experience that members of the team have directly working with building energy controls in the field, and also with speaking to experts and people in our network and looking at the available material, and then we modeled that into the energy model. But as you can imagine, it's quite a complex process. That is a sort of summary of the process. And then you're asking, as you said, building requires continuous commissioning, maintenance, etc., to meet the expected energy performance. Did you assess the cost of this? Did you include? Yes, we did assess the cost of this, and yes, this is included in the profitability estimates. Having said that, I have no doubt there's plenty of scope to elaborate and improve those estimates, there's limits to what can be done in a study of this kind, as I'm sure everybody appreciates. But yes, we did make some estimates of what those were.
Okay, Paul, thank you very much. I don't see more questions at this stage, so I would propose to adjourn here. Just repeat my question to everybody to please fill in the little questionnaire I'm sending you right now, 1 minute after this presentation. There you can give more feedback and questions for consideration on the publication, and also give your intention for and the level of participating in further actions we might undertake. So Paul, thank you again for your clear presentation, and then we shall hereby adjourn. I thank everybody for attending this webinar, and I'm sure we keep in touch in the coming days. Thank you very much.
Yeah, thank you, everybody.